So let's consider an application. So let nu n be the number of prime numbers dividing n. So for example, nu 60 is that 60 is 2, 4 times 3, 2 squared times 3 times 5. So 2, 3, 5 are the 3 primes that divides 60. So we have 3 here. On the other hand, nu of 81 is 3 to the 4, so only 1 prime divided, which is 3. And Hardy and Ramanujan in 1920 show that this nu n is close to log n for almost all n. So meaning that this happens. If you take 1 and x, and then you 1 and say m. So you consider all the numbers which satisfy this, or the n between these two which satisfy this. Then the number of such n whose nu value is close to log n is almost everything, except the small fraction. And the proof they give was rather complicated, but later Turan gave the much simpler proof using the probabilistic method. So let's see what Turan proved. Let's say this omega n is a function which goes to infinity arbitrarily slowly. Then, so this could be any function goes to infinity in a slow way. The number of integer x between 1 and n such that u of x is much deviated from log n in a sense that the deviation is at least the omega n times square root of log n is a small fraction, omega n. Little of n. So meaning that, so here let's write this way. So between 1 and n, you check, let's say here. So you might be a bit confused that here I said log x, but here we have log n. But most of the x here, if you take, let's say you take a square root of n, you just throw away the numbers between 1 and square root of n. That's just small fraction. That's little of n. So that's a very small fraction, so you forget it. But all the x above it, log x and log n are almost same. The difference between two are just constant, negligible. So log x and log n are essentially same for any number between these two. So this and log x, this statement are not really different. So how we want to proceed? So we want to show that most of the number x satisfy this. So maybe we choose this x from this bracket n at random. So x is something we choose at random. And we want to count the number of primes dividing x. Then again, what we want to do is we want to define some random variable which measures what we want, and then we want to write this as a sum of the more simpler thing. So this gives an idea, motivation of defining the following. So let x be a number between 1 and n, which is chosen uniformly as random. And for a prime number p, we let xp be 1 or 0. This is 1 if p divides x, and this is 0 if not. Then the summation of xp actually estimates, not only estimates, but it gives new x. But for our computational, simplicity, let n be, n to the 1/10, say, and we let x be the random variable, which is that p is smaller than m, which is prime number, and then we add xp. So we count the prime divisor of x, small x, which is at most large m. Then what we know? Every x in here has at most 10 prime factors larger than m. So we can just forget them, but we wouldn't lose much. Meaning that we want to estimate this new x, but this x, this random variable x, is actually a good estimation of this new of x, because this lose less than 10 prime factors from, actual x. So we can focus on estimating this x instead of nu. So we can now forget nu, because x and nu are pretty close. And then difference is at most 10, and 10 is nothing compared to here. So that's an error that we are willing to take, much less than the amount of error that we are willing to take. Then now what we do? We want to do two things. First, we want to estimate the expectation of x. And then we want to show that it is very concentrated around its expectation. For that, we need to measure its variance. So let's consider the expectation. Then again, this is the summation of the indicator random variable. So its computation is not so difficult. For all prime p at most large m, what's the probability that xp is 1? This is, there are n divided by p, taking floor many, this many multiples of p, and out of n choices that we take. So x is from between 1 and n. So there are n choices. Out of that, this many choices are actually multiple of p. So this is what? You just take this. This is essentially 1 over p. But because of this shielding, there are certain error term, but which is at most some constant times 1 over n. And well-known fact is that if you take summation of primes, at most x, then this is log x plus some constant. So this is log, say, m plus some constant, because this part, if you take it, then you get this. And this part, if you take I mean this many, then that's at most 1. I mean at most some constant, because m is smaller than n, so this is constant, so it contributes to there. And then because m and n are, I mean, just this, so if you take a logarithm once, then you get this, and if you take the logarithm again, then this is log n plus 1 over 10. I mean log 1 over 10, which is just constant, so it's observed here. So we now have so this is a known fact that I will just use. So we now have this estimation on the expectation. Now we want to show the variance. What's the variance of indicator random variable? So we know that I mean it's easy to actually compute for this indicator random variable. The variance is, you can just compute that the probability that this xp is 1 times probability that xp is 0, and you can actually compute that this is nothing but 1 over p times 1 minus 1 over p plus some constant times 1 over n, big O of 1 over n. And now what do we have to compute? We have to compute two things: summation of this variance and summation of covariance. So let's first compute the summation of variance. And summation of all the variance of this indicator random variable is from here. This is essentially summation of 1 over p plus the later term is just the at most constant, because you add capital M many, at most capital M many this term, which is constant, and here is contributes the summation of 1 over p squared. And we know that this converts. Even we don't care about the prime. If you just add from 1 to n 1 over p squared, then it's infinity. See, it's bounded by some constant. That's something we know. So we have this inequality. And now we want to measure the covariance. So let's say PQ are distinct prime. And when does this becomes 1? This happens if and only if PQ divides X. So what's the covariance? Now covariance is expectation of XP, minus expectation of XP times expectation of XQ. And because of that, we can actually measure the first probability, which is n over PQ. You take the floor and then divide it by n. And here is n over P divided by n. Taking floor. N over Q taking floor divided by n. Which is, if you compute, this is 1 over PQ minus 1 over P plus minus 1 over n times 1 over Q plus minus 1 over n is just the number which is quite small. So again, if I write something plus minus something, so this indicates that this is a number which is at least this and most this. This is not. So 0 plus. So it just indicates that its absolute value is small, smaller than say this. Then what's the covariance? Sum of the all covariance xp xq is m most. So this absolute value is m most 2 to the n, 2 over n plus 1 over p plus 1 over q, and p and q are different. And for specific p of 1 over p, the number of q, how many times do we have this in this summation? For fixed p, the q has at most m choices. So 1 over p term actually appears less than m times, the capital M times. So you can actually make sure that this is at most this number, 4 capital M over n times summation of 1 over p. Again, what was m? N is this. So, and this is at most log n. So you can actually show that this is a very small number, n to the negative 9 over 10 times log n, which is little of 1. So now we have the summation of covariance. So we just show that this part is little of 1, and this part was log n plus some constant here. No, here, not here. Where is it? Yeah. So, hence what we know, the variance of x is nothing but log n plus some constant. And we use Chebyshev. Chebyshev inequality gives that for any lambda positive, what we have, the probability that x deviates from log n by lambda times log n is at most lambda to the negative 2 plus some little over 1 term. So taking lambda as our omega of n, the function that goes to infinity in an arbitrary slow way, then we show that this happens with a small probability, little of 1 probability. And as x and u are, the difference is at most 10, so which is negligible in terms of this. So this actually concludes the theorem. So that except the little of n many, the number of x in bracket n satisfying this is, essentially everything except the small number of terms, numbers. So that's one application of the Chebyshev's inequality and the second moment method. And in next video, let's consider one more example. And yeah, we will see. Not just one more, but maybe in next video just one more. But after that, we will also see several more examples of, second moment method.